All right, so as mentioned, I'm a partner and data scientist at Datascope. If you're not familiar with us, we're a data science consultancy based in Chicago. And we help our clients try to determine what they could and what they should be doing with data, and particularly with the cutting edge of data science. And then we help them execute on it by consulting, by building prototypes and tools. Today, I'm going to talk about a particular case study that we've worked on. Our work with the Research Corporation for Scientific Advancement, or RCSA. And as part of that, I'm also going to give a high-level explanation of one of the techniques that we used called simulated annealing. Simulated annealing is a stochastic optimization technique. And I'm also going to talk about our vision of the role of a data scientist and how they interact with the people who they're serving. I didn't choose this project because it's the biggest data project we've worked on, or it's the most impressive name. In fact, this is probably the smallest data project you'll hear talked about at Strata. We didn't have to do any fancy infrastructure stuff to pull this off. But I picked it because, rather, I think it's a really cool example of a creative application of data science and of this interaction of how you work with, how a data scientist works with a client and vice versa. So speaking of our client, this is Richard. Well, this is my rendition of Richard. Richard was one of our first clients, and we've been around for coming up on 8 years. So we've been working with Richard for a long time. We were lucky to have such a great client as Richard early on because Richard's a fellow nerd. Richard has a physics PhD, and I would dare say he's as intensely curious as many of the people at Datascope. Since then, we've learned how to work with people who don't have physics PhDs, but regardless, Richard works for RCSA, and one of the things that he does for them is he runs a conference series for scientists called Scialog. And Scialog is a series of conferences run at Biosphere 2 in Tucson, Arizona, hence the pretty picture. And it's also a series of grant awards that are tied to work that gets proposed at the conference. So if you're a scientist and you go to this conference and you come up with something you want to work on there with somebody else, you can get money from RCSA to work on it, which is pretty cool. So when Richard came to us, he was telling us the goal of these conferences is to facilitate collaborations. It's to connect people and to sort of catalyze new areas of science. It's to bring people together from across the sort of different silos and different parts of academia that they may be from. They've run 7 of these conferences across a few different topics, ranging back to 2010. I'm going to talk mostly about the conferences since 2015 in this talk because we changed the survey methodology between the two, and so it's a little bit apples and oranges, but we've been working with them since before then. And one of the things that makes, well, there's a lot of things that make Scialog different. They're quite a bit different than your typical conference. One of those things is those topics that you just saw up on the screen. So the Scialog conferences, for example, the first one we worked on, solar energy conversion. You might expect that at a solar energy conversion conference, you have some electrical engineers, you have some material scientists, the kinds of people who are thinking about how does a solar panel work or something like that. But you might also have some physicists because they might be thinking about energy in a more general and systems level way. And you might also have some people who are biologists because they're thinking about how organisms can take the light from the sun and turn it into usable energy. And so you're bringing together these people from across disciplines to talk about a big problem. And that's one of the things that makes these conferences different. Another is that they're very small. So they have 40 to 50 junior scientists. These are people who are typically, they don't have tenure. They're probably like assistant professors, but they're really kicking ass in the research world. And then you have like 10 to 15 senior scientists who are going to facilitate sort of the rest of the conference and help bring that perspective. The other thing about these conferences is that they're invite only. So to control these things, to get a good balance of people, to get people who are doing research that's relevant to the topic, they specifically handpick who's coming. And finally, they have an unconventional format. So unlike a place like Strata, where most of the time is probably spent in things like tutorials and sessions where there's sort of this audience speaker dynamic, at Scialog, most of the conference is made up of these discussion groups where people are in smaller groups with their peers and they're talking about problems and talking about their work and how it might relate to, how they might relate to one another. So the first thing that Richard wanted to know when he came to us in 2010 was, how well does this work, right? is this actually helping us achieve those goals of catalyzing new collaborations between attendees? So the first thing that we did with him was we sort of defined what are the levels of connection between people at a conference. And the sort of base level is unawareness, right? So between any two people at a conference, maybe they've never heard of each other, they don't know who each other are. That's the base case. Beyond that, you have awareness connections, right? So maybe you've heard of somebody, you've read something they've written, you maybe know where they do their research, and these are directional connections, right? So I might know who that person is, but that person might not know who I am, or vice versa. The next level up is a discussion link, right? So these are people who have had like a meaningful conversation about science at some point, or about whatever the topic of the conference is. And then finally, you have people who have collaborated, right? And this is what they're trying to build, these links. People who may have co-authored papers together, people who have helped each other out with their research, they've worked together in meaningful ways. So because this is such a small event, the data collection for this was relatively simple. It was a survey. So all the blurred out stuff on these slides you'll see, those are names. You can imagine if you're attending, you see everybody else who's going, and you can mark at what level do you know that person. So have you talked to them before? Do you know who this is? We get that for everybody. Where that starts to get more interesting is once we have that data, you can think about it as a graph, right? So here is what the attendees of the 2015 Molecules Come to Life conference looked like before they went to the conference. And the different link thicknesses here you can see, the fat ones are those collaborations, the medium ones are the conversations, and the thin ones are the awareness. And I wanted to show this one because they were the least connected group before the conference because they're kind of from all over. You have biologists and chemists and everything in between here. But where this really gets interesting is when we run the same survey 1 year later, after they've been to this conference together, after they've had some time to have a chance to work together, you can see the change. So that's the effect that this conference had on this community of people. If you miss the animation, here's the before and after. So this isn't a perfect experiment, right? Because they only have the one conference. They don't have like a control conference where they didn't do it in a specialized way. So we don't know for sure that this is like doing way better than if you just put these 60 people in a room and had them listen to talks all day. But it is a way of measuring the impact of this event. So the impact, speaking of this particular conference, there are 118 new conversation links between people at this conference. There are 17 new collaborations, and that's as many existed as before they came in. So there are twice as many collaboration links in this network, in this community of people, after this conference as before. And that 17 number may look kind of small, but when you consider that each collaboration involves at least 2 people, and there's only 50 or so junior people at this thing, over half of attendees actually formed a new collaboration with somebody else who was there. So Richard was pretty happy with this, and we've run the same survey at 3 conferences since then and seen similar results each time. One of the caveats being that when people come to a conference and they already know each other, the potential is lower for them to form new connections. And so naturally, you're not going to see as much. But as a percentage of the possible connections, like the connection growth, that's pretty steady across conferences. Where this really got interesting, though, is when we shifted our thinking from measuring to improving. So we were measuring the impact of these conferences in some way, right? But we realized then that we could probably do better than that. We could maybe engineer these conferences. We could engineer the discussion groups that are happening during them and make sure that we're putting together people who don't have awareness of each other or haven't talked before, right? So I mentioned that the format's unusual at Scialog. Here's a little bit more of a detailed example. You have these mini breakout groups of 4 people, right? They have no topic. So you just put 4 people together in a room. They talk for, I don't remember exactly how long they are, but consider each of these dots a conference attendee. And they do this 3 times throughout the conference, and each time the groups are scrambled, right? So people move around. You have 3 different groups. In order to improve these groups, or in order to find the best ones, we need to start with some way of quantifying whether they're good or not, right? And one way of doing that is just focusing in on one and saying, is this group good? And if we can do that, then we can do it for all the groups, all the discussion groups. So here's where that data that we gather from the survey comes into play. We know the connections between the people in this group. And because of that, we can sort of assign a score. We could say, well, these two people who are aware of each other, let's say we give that a penalty of 1, because ideally they just wouldn't even know who this other guy is. Because if they know them, then maybe they would have talked to them in the past. Like, if they don't know them, there's more opportunity for there to be something there that we don't know about. But if they've talked before, that's even worse, because we're trying to foster new connections, new conversations, right? So we'll penalize that more. And if they've collaborated, well, that's the worst of all. So we penalize that more. And you'll notice that these are sort of ramping exponentially, right? We care much more about avoiding collaborations than avoiding awareness. So we could say this group has a terribleness rating of 7. So if we wanted to make it better, maybe we could put somebody else in there, swap out this guy, and put in this new guy, B. Nobody knows who B is, so the terribleness rating of this group is 2. So this seems like a simple enough problem, and oftentimes the place you would start with something like this would be brute force, right? You just try every configuration of groups, you measure the terribleness of each one, you pick the best one, and you're golden. So we did some back of the envelope calculations on that. And unfortunately, there's like 10 to the 40 different ways that you can make these configurations of groups. And sometimes you see, okay, so you'll see numbers like this, and this looks scary, and then you remember that computers are really fast, and it's like, it's not really that big of a deal, right? So we did a little more math on the back of the envelope. The envelope is getting crowded at this point. If you take the fastest computing cluster on Earth, the Sunway Taihu in China, and if you assume that determining the goodness of each group takes at least 1 calculation on that computer, which is probably a pretty conservative estimate, it would take this computer quadrillions of years to brute force this problem. And this is not like a complicated problem, right? It's basically trying to deal a deck of cards into hands of 4 and trying to do that every possible way. But the way the combinatorics work out on this, it just kind of blows up. It's of sufficient size that we can't just try everything. And this isn't unique to this type of problem either. You see this all the time in things like this, where even with just 50 people and putting them into groups, this gets to a scale where you can't try everything, right? Okay, so if we can't try everything, we don't really care about trying everything, really. What we care about is finding the best thing. So you might turn towards optimization. And the idea behind optimization is, rather than trying everything, let's start with a random thing. And if we can just keep making that thing slightly better, so if we can start with a random group and just keep making moves to make that group a little bit better, then we'll end up at the best group eventually, right? When you can't make moves anymore. So this is kind of a visualization of, if you've heard of like gradient descent, that type of idea, trying to find the optimum thing if the terribleness is like the y-axis here. The challenge with that on this problem is, when you consider that example from earlier, we have this group with a terribleness rating of 7. We make a change, and it gets better, right? If we make another change to this group, now this person has a link to somebody else in the group, and it's a worse solution. We make another change to this group, we end up with the best group that we've come up with so far, right? We make another change, we swap this guy out, we end up with the worst group that we have so far, right? So if you were to kind of continue this, and these are all only one person different from each other. So I'm kind of simplifying it down to 1 dimension here. It's like a lot bigger than that, and we can't fit it in our brains in reality. But if you were to sort of extrapolate this, you end up with not a simple like thing that you can roll a ball down here, but something that looks a lot more like this. And if we try to use a traditional optimization technique on this, we start somewhere random and just keep finding the better thing. Depending on where we start, we may end up with a great solution, but chances are we'll end up in one of these other little valleys that may not even be in the top like 50% of solutions, right? So how do we deal with this? This is where simulated annealing comes into play. So simulated annealing, as I mentioned up front, is a type of stochastic optimization technique. Other ones you may have heard of include genetic algorithms. Sometimes these are also called meta-heuristics. But basically all that means is it's an algorithm, it's a search algorithm that has randomness introduced so that you don't get caught in those local minima, so you don't get caught in those little valleys. Now what you lose when you use something like this is the guarantee that you'll find the absolute best solution. The math doesn't bear that out. There's no guarantee that you'll end up in that lowest best group, least terrible group, I should say. But you're going to end up with better solutions than if you tried to apply traditional optimization to a really rough problem landscape like this. So the name simulated annealing sounds fancy. It comes from metallurgy. Annealing is when you heat and cool a material, like a metal, to try and reduce the defects in it. I'm not a metallurgist, and the metaphor to me is kind of tenuous, but maybe you'll kind of see where the people who came up with this sort of got that idea from. So the simulated annealing algorithm is actually really simple, and I'm just going to run through the entire thing right here. We'll start with a few variables. So we have our groups down here. This is like our current state, right? We have the temperature. So this is a new one, right? Temperature you can kind of think of as like a willingness to explore. So early on in a problem, the temperature is high. We're willing to try a lot of different things. As we get towards the end or get towards an optimal solution, we're less willing to just keep trying more stuff. We want to settle in on the best answer. So the temperature will change. We have the current terribleness of those groups, and we have the terribleness of the state of the groups before that. And you'll see what I mean by that in just a minute. So the first thing we'll do with this algorithm is make a random move from our current state. So in this case, that means taking two people in different discussion groups at the conference and swapping them. So we make that move. You'll notice that the terribleness of all these groups changed. It actually went up. So we check. If it's better than the previous one, we're just going to keep it, right? Because you found a better group than you had, so we want to stick with that. If it's not, though, here's where the stochastic piece comes into play. There's a chance that we'll still keep it, depending on that temperature. So I mentioned right now the temperature's high. We have a high tolerance for trying new things, basically. And so we sort of roll the dice, and we'll actually keep this less optimal solution. If you think about why we would do this, because that landscape is rough, if you think about being at one point on the possible state of the system, and you end up on something worse, on the other side of that, there may be something even better. So you might want to take the chance and say, well, I just need to make one or two more swaps, and I'm going to get to a way better solution than I was where I started. So we'll keep it in this case. When the temperature gets low, we stop. Otherwise, we just reduce it a little bit and repeat this series of steps again. So we'll make another swap. The terribleness is better this time than where we started, and better than where we were at the beginning of this, and so we're just going to keep that one. So much like a cooking show, I'm going to fast forward to the end of this now. And now if we end up with a system where our temperature is really low, our terribleness is much better than where we started. Now at this point, if we're on step one again, we make another random swap, and the state of this system is much worse, we're probably not going to keep it anymore. Because the temperature is much lower now, we've sort of lost our desire to keep exploring. So we'll swap it back. Here's an animation of this, full disclosure, slightly modified from the Wikipedia for simulated annealing. But this will show you a little bit where that temperature metaphor comes from. So it's trying to find here the lowest point in this curve. As the temperature decreases, you'll notice that the thing moves less. And early on, we're willing to sort of bounce around and move a lot, much like molecules in a hot material, right? And as the material cools, there's less motion, right? We're less willing to move all over the solution space. So one of the really cool things about this technique, it's not just for like things like choosing like groups of things at a conference or wherever else. You can use this for all kinds of applications, and it's been used for things like circuit board designs. So trying to figure out, you have all these chips that need to be wired together in a certain way. I want to fit them inside of this thing. You can have a computer decide, okay, how do we actually lay those out, given some set of constraints and some set of a measurement of goodness, whether that's how much space they take up, sort of how risky it is to manufacture and things like that. They're used in the financial world for stock trading rules. So if you think of your current state of your portfolio and the conditions of the market and things like that, it can sort of tell you in which direction might you want to move. It really can be used for anything where you can define a state, a transition of that state to another state, so like a swapping of people in groups, and some measure of goodness. And that measure of goodness doesn't have to be like a continuous function or anything. It can be just kind of any metric that you can come up with. That's not to say you should apply this to everything, but it's a very flexible technique. It's also a very tweakable technique. So what I showed was the most simple example of simulated annealing. In reality, a lot of times you'll sort of add some additional features on top of that. So for example, you might want to make smarter than random moves. So rather than just taking two people in different discussion groups and swapping them, we might want to target the people who are problem people, the people who are in a group where they've collaborated with everybody else in that group already. You might want to change the cooling function. Sometimes people will reheat and cool these things. So they'll say, you have freedom, look everywhere, I'm going to take that away. You have freedom again, I'm going to take that away. Or they'll do it in like an exponential fashion or in a linear fashion. And that changes sort of how it settles in to those things. And that'll differ by problem and the sort of the space of your solutions. You can save the best state so far. That's generally a good idea to do, but also you might restart from it every once in a while to say, okay, we started from here and we tried to find something better and we didn't. Let's go back to that because we know that's good. You might repeat this many times from different random starting states. This can be kind of a way that you can take this problem and do it in parallel if you're trying to do it across a bunch of different things. So there's lots of ways to tweak this, and as a result of that, I have to give a warning. For data scientists and for managers of data scientists. There's a reason, the reason that I'm giving this warning is twofold. One, that you might, depending on your problem, have to tweak this algorithm a lot to get the results that you want. The second warning is that you might not have to, but your data scientists might do it anyway. Because it's very tempting to just try and make that thing a little bit better, a little bit better, a little bit better. And so I think it's really a good idea when you're doing this type of thing to decide what's acceptable ahead of time so that you know when to stop. Because you could tweak this and make it better just kind of incrementally forever. And so you have to decide at some point to cut it off. So I'm going to come back to this idea of terribleness. I've been saying this hard to say word quite a bit. The technical term for this in optimization, it goes by a few names, which is part of why I abstracted it, which is probably how things end up with more names. But anyway, it's often called a cost function or an objective function or sometimes an energy function. And to me, this is a good example of some of the skills that a data scientist, I think, needs to have to do good work. One of those skills is defining the needs of your client or helping them define their needs. So early on in this project, we talked to Richard, and Richard told us, I want to minimize how connected the people in each group are, right? So that was that thing that I was showing you earlier. He also said, I don't want anybody to be in the same group with somebody else twice, or more than twice, right? Because you have their connections coming into the conference, and then if they're also connecting at the conference, that matters just as much. So that's an additional constraint. We don't want people to talk to the same guy 2 or 3 times throughout the day when he could be talking to somebody new. So we come up with these things talking to Richard, right? Going through the design process, interviewing him, figuring out what his needs are. And we do this with every client that we work with across many different industries. It's important to figure those things out ahead of time and then to do our job of converting that into math or code as data scientists, right? But only after you've identified the needs. And we find that on a lot of projects, the best way to do this is not to do this once, not to do this translation once, but to do it iteratively. So if anybody was here for the previous talk, you saw my colleague Ermac use this diagram, but we started by asking what Richard needs, right? And we came up with those bullet points. We built our first prototype, and we looked at it and we said, okay, well, these results don't look great. These could do better, right? Maybe we need to tinker on the optimization algorithm a little bit more. So we go back to the drawing board and tweak it. We get some results that we think look better, and we say, what do you think, Richard? Here's our preliminary set of groups. And Richard says, those are pretty good, but I don't like this aspect of them. For example, when we were optimizing some of the larger discussion groups for one of these conferences, Richard was seeing instances where there would be like a room with like 9 men and 1 woman in it. And he was like, that's less than ideal. Could you try and work that in somehow? Could we avoid those? There's probably other groups, right? Or he would see things where there were like 9 physicists in a room. And he's like, that's also less than ideal. I don't want a room full of physicists. You never know what might happen. But also, the goal of these conferences is to be bridging these gaps, right? If it just looks like a physics conference, then we're not doing our job. So we learned these things by showing Richard results. And generally, I think people aren't good at putting what they care about into numbers just off the bat, right? But when you show them a concrete example of something, when you show them the output of a model, it becomes real for them. And so they can articulate, these aren't things that Richard thought of ahead of time. And there may be things that would have never come up in our initial conversations with him. But by showing him results and getting his input on them, we could fine tune this model. So we go back to the drawing board again. we tweak the objective function, work on that prototype, run them again, and Richard's happy. I'm going to zoom out a little bit because I think it's interesting to think of this cycle as an optimization technique of its own. I think if you work in an iterative fashion, it's almost like you're trying to roll that ball down the hill, right? You're trying to arrive at trying to figure out what direction do I go to arrive at the most optimal project outcome. Now, I think you see this pattern repeated across many different areas. You see it with agile programming. You see it with the lean startup method in entrepreneurship. You see it with human-centered design in the design community. You see it in the scientific method. And all of these methods see great success no matter what domain they're applied to. And I think that that's because there's sort of this core of optimization, of checking and moving in the right direction frequently that is at the heart of these things. But this is getting really meta, and that's probably another talk for another time, maybe at the O'Reilly Design Conference next year, if somebody can hook that up, I don't know. So let's get back to RCSA. Did this work? So if we look at the results from our 2015 Molecules Come to Life conference, which was the first one that we did the optimization for, in 30 out of 39 group discussions, nobody in the group had ever heard of anybody else in the group that they were talking to. So in only 9 of these things were there any awareness links at all. In every group discussion, nobody had spoken or collaborated with anybody else in their group. So these were all people that they'd never talked to before. In each group, there were 2.6 different disciplines. So given that these are groups of 4, that's pretty good. You're going to have at least like a physicist and a biologist and maybe somebody else. And each group also had at least one theorist and one experimentalist. So we also had that data, sort of like how do they approach their study? Are they somebody who's more of a thinker or more of a measurer? And then, again, we've run this at 3 conferences since then and seen sort of similar success each time, depending on how connected people were coming in. The people at the conference, the attendees, also really liked it. So when you compare the mini breakouts that we optimized versus the regular discussion sections where we didn't do any optimization at this conference, on average, people thought they were more important to the success of this conference than the typical discussion groups. And Richard was happy too, because they got more proposals out of this conference than they'd ever gotten at something like this. But we didn't stop there. We kept iterating, and we did this at further conferences. So I mentioned these topic groups, or maybe I haven't mentioned them, but in addition to these little groups with no topic, they have slightly larger groups that have topics attached to them. So things like tissue mechanics and evolution. If you think you're at a nerdy conference, you've never been to a sciolog. But these are groups where if we're trying to optimize these, we care about all the things we cared about before, but we also want to make sure people are talking about topics that they actually care about, right? We don't want to end up in a group where you don't care what people are talking about. So we included that in the survey. So on a scale of no way to really into it, they could indicate which topics they were interested in. We add that to the optimization on top of everything we were doing before, and it's just an additional factor that gets taken into account when we make these groups. Another thing we added to the survey was the ability to indicate desired connections. So you see somebody else at the conference, you're like, oh, I really want to talk to that guy. You can click that on the survey, and we'll take that into account when putting the groups together. You could also nominate people who you think might be experts for one of the topics that's going to be discussed. So if you say, I'm interested in vitro mechanics, this guy would be a great person to be in that group. You can nominate them in the survey, and we combine that data with the preferences on what you want to talk about so that the people who are really like key researchers or experts get placed and they get a little bump from their peers to say, this guy needs to be here if we're talking about this. So a lot of these things that we came up with were either requested directly by the attendees of these conferences, or we designed them in collaboration with RCSA to address shortcomings that we'd seen in the previous conference. So since we designed the survey software, we were able to add this in and sort of make sure we had the data at hand when we're running the optimizations to do a better job. So I feel obligated to talk about how this might work at some place like Strata, where you have not 50 people, but 1,500. So we can't obviously survey everybody, right? You can't just go, I mean, I guess we could, but I don't know if anyone would come if they had to fill out 1,500 people and say who they knew. But But we could probably pull in some information like from social media or from the RFID stuff that's in your badges if you went last year, right? Maybe you don't know about that. You should read the back of your badge. Or we could use a survey with a representative sample, right? And say, if you're interested in talking to this guy, there's like 5 or 6 other people in similar positions at similar companies. You might be interested in talking to them as well. There's also the issue of format. I don't know how you would make like groups of 4 out of 1,500 people where you would have something like that. You need a lot of small rooms. But maybe it could be in a separate opt-in track, or maybe it could be something like email introductions ahead of the conference rather than groups. But to conclude, I think there's a few things to take away from, or that I've taken away personally from like this work with this client, and that I think that you can take with you whether you're a data scientist or somebody who works with them. For one, optimization is not just for straightforward math problems, right? It's kind of flexible, and especially for things that are kind of arduous to figure out by hand or are driven by uninformed systems right now, I think it's really promising. Everybody is talking about classifiers and predictive analytics and deep learning and artificial intelligence. And for some reason, I think optimization is less sexy than those. But I think there's actually a lot of cool potential applications of it that I think people should be thinking about. I think in general, data science, this is true for data science as well. And when you ask somebody what's exciting about data science, they say self-driving cars, and they say recommender systems, and they say image processing. And they probably don't say event planning, right? But when you take this sort of quantitative lens on a field that hasn't been touched by it before, I think generally things come out of the woodwork. We've seen this in our work. Most of our clients are not the big tech companies. They're mostly companies that haven't been touched by data science. And as soon as you start thinking about how might we do this in a better way, using data, using methods like this, you start to come up with some really cool project ideas. A great data scientist acts as a translator. So I mentioned that Richard is a big nerd, but he didn't have to think about most of the stuff that I just told you about. He didn't come to us and say, I want you to run a stochastic optimization on my conference. He just said, do you think we could make these groups better? And I think we could use this stuff we're already collecting to do that. And we said, yeah, we think so too, and we'll handle how you take care of that, and we'll work with you to figure out what the objective is, to figure out what are we trying to accomplish here and how do we do it using data and using the methods. Another thing to take away is that iteration drives improvement on these things. Repeating it drives improvement on these things. By showing things to Richard, getting feedback, and working it back in, we ended up with a better model. By doing this at multiple conferences, we ended up with a better data collection strategy to get more things during the survey that helped us make better placements based on what the people attending cared about. And finally, if you have the data to measure something, you have the data to actively take steps towards improving it. So these projects started as measurement things, right? They started as backward-looking things. They started as things where we just wanted to see what impact does this conference have. But if you have that, then you know that you could actually apply that to planning the conference. It becomes something integral to the way that this thing runs, and ultimately it ends up with a better result than if you just kind of like look backwards and see how we did. You can be more proactive and in this way, and I would encourage you to think about things that you're measuring now where you're not actually using the data that you are gathering to change that process or to make it better. Because I think there's a lot of those out there, and they're really exciting opportunities. So that's it. I think we have a little time for questions. It's like 12:25 or so, so 5 minutes or so. My slides are up at that link if you want to go check them out. My contact information is at the bottom if you have additional questions or if you want to get in touch. I'll be here through Friday if people want to meet. So thanks for your attention, and have a good rest of your conference. People have questions?
Let me just ask one to get started.
Sure.
One of the things that was most fascinating to me, you were able to tell, is it Richard who was your client? You seem to be able to help him get at a better understanding of what he in fact wanted himself.
Yeah.
Is that a common pattern you see for your customers?
Yeah, so the question was, in doing this work with Richard, we helped him clarify like what he wanted as much as sort of like implementing that in what we worked on, and is that common? I would say definitely, especially if we're working with people who tend to not think on that strategic or metrics level. Just starting with something and then seeing the results, and like I said during the talk, like showing them something concrete. I think that's why we prefer to work in this way, because a lot of times the goalposts will move if you don't work in an iterative fashion. Like if you just say, we're going to figure out everything up front, and this is like the waterfall thing in software engineering, right? We figure everything up front. We're going to have this great plan. We're going to think of everything, and then we're going to do it, and then it's going to be done, and that's it. And I think if you do that, you might end up at the end and somebody's like, but I didn't put this thing in the plan at the beginning. And that's why we advocate working in this iterative fashion, because a lot of times people's needs do shift over time, and they also just come into greater clarity as they're starting to think about and see things in a more quantitative manner. Yeah?
So it seems to me that the connectedness is one of the things that got measured in the optimization problem.
Mm-hmm.
There were a lot of other sort of properties that probably went into. So you kind of started off with that objective function. However,
Yeah.
The objective function seemed to get much complex towards the end when you take into account like gender balance and
Mm-hmm.
balance of expertise and things like that.
Yeah, so the question was about sort of how the objective function evolved over time. And the example I gave at the beginning was just the connections.
Right.
But over time, we added more and more things to that, including topic preference, including nominations and things like that. Yeah, so the function definitely got more complex by making that function a piece of software, right? A series of like nested functions and modules that connect to each other and organizing that in a good way. It didn't end up being this like big math thing that was untenable to manage. It was just something that, you know, each time we would add a little bit more to this thing, and we were able to sort of like keep it under control and tweak it as we learned. But yeah, it definitely did evolve from a very simple description of what we wanted to something more complex. Part of it too, I think, is just showing that you can do it on the simple thing. People start to dream a little bit more. Richard's like, oh, could you? Well, so all right, so you already did this, right? That it works. And we were like, yeah. And he's like, could you do this other thing? And we're like, absolutely. And they might not at the beginning. People are maybe sensitive to like asking for too much because they don't know whether you're even going to be able to pull it off. But I think when you can sort of prove that and say, is there anything else? Is there anything you don't like about these? That's another reason we advocate for sort of working in that cycle. Do you have a question?
I was wondering what other topics you studied in the surveys after an event to just kind of understand the quality of the event. What other insights?
So the question was about what other topics are included in the survey, like post-event, to learn about them. So part of that I actually don't know about because Richard ran those surveys, like separate. They didn't hire us to do the survey stuff. I know in some of the earlier conferences, some of the things we were looking at were what were the sources of those new connections. So if somebody fills out the survey and then as they're filling it out, we know, okay, this person went from you didn't know them at all and now you're working together. We could actually ask them, where'd you meet this person? Do you remember? And that's part of where I mentioned the survey methodology change, because we used to do them right at the end of the conference. And so it was fresh in people's mind. They're like, oh, I met this guy in a discussion section, or I met this guy in the hallway. So we did do some additional survey stuff where we were looking at what types of activities at a conference tend to increase connections. It's hint, it's not talks like this one. It's like undirected discussion, and it's part of why over time the format of this conference has shifted towards discussion groups and things like that, because they saw that those coupled with the promise of money, if you could come up with something to work on somebody else with, were the things that really motivated people to actually like get outside of their bubble and form new connections. I think is that the wrap it up sign? All right, I think that's it. Everybody enjoy your lunch and thanks for coming.